Thank you very much, and thank you for the invite. So, as it was mentioned, what I'm going to be doing is presenting some work that we have been doing around data integration and data. So, I think the previous two presentations have been really nice in terms of giving context for what it is that I will be talking about. And I started this presentation by the title, which is meant to be provocative, which says, Building of the Future. And I would like to invite all of you to think how that building of the future will look like and will be different from the building of today. So maybe spend 10 seconds thinking about that. Is it going to have a different shape or form? And how does it look different, or how would it look different? And I think the way of answering that is kind of going back to the basics. What are we building buildings for? I think there has been the presentation this morning that they are meant to provide shelter, they're meant to provide spaces that we interact, we collaborate, and they are meant to facilitate human interaction. So if I have to answer in that discussion around data, what is it that we're trying to achieve? We're trying to create those spaces and make them better. And we have been doing that all along, so that is not something that has changed or fundamentally different from what we did. What I would like to argue is that data can be a complementary way or an additional way by which we can achieve that slightly better. And if we look at statistics, if we look at post-occupancy evaluations, we might very well create evidence that our buildings are not working the way we're intending them to do. So, for example, there is terms like the performance gap, which is the mismatch between what we design and what we achieve. There is there are studies around lighting, comfort, whatever have you, and how well or not well we're doing. So what I would like to discuss is I would like to discuss or to tell you a story around metadata. And I will do so in a very concrete example. So what we have been working with several partners in the context of the European project has been trying to understand how to implement these technologies on some buildings. And so these are some buildings that have been recently developed at UCL. So this is at our East London campus. And UCL spent $500 million in terms of developing those buildings. Now, what has already been mentioned is that we are looking at creating spaces. For example, this is a mixed-use building which has student residences and then lab spaces. The other is a teaching space / lab space. We're looking at creating spaces that people are going to get together and work together and live together and learn together, right? So how can we go about doing that? And the question is, what role does data have to do with that? So here's one example to kind of highlight the complexity. It is a typical building that you would find, and kind of many of the technologies that are there are things that are very bread and butter for everyone here. But then, that problem around complexity emerges very quickly. We have a system, and that system is a complex system, and it's a complex system of systems. And in fact, that complex system of systems has a lot of uncertainties, and these uncertainties tend to be humans, tend to be contractors, tend to be delivery processes, tend to be the whole ecosystem around how we go about delivering something. So we, or the university, tries to collect data to understand how that process has worked. And in reality, what we find is that there is a quite significant mismatch between what we plan and what actually is happening. And so there's a question around how we can benefit and kind of productively use all that information as a way of improving our understanding, but also achieving the main purpose, which is serving the users and serving the occupants and creating spaces that are good for them. And I think, and I would like to highlight that delivery process, every AI that might come, and kind of I think maybe I'm going to somewhere in between what was discussed in the first presentation, has to be serving the purpose, and that purpose should be to support a specific process or a specific task. And to be able to build such AIs, it would be quite interesting to understand what those tasks could be. So here's an example, and this is an example of data that are being generated, or even metadata. And this is the building information model of that particular building, so one of them. And what you can probably tell, or you can probably infer, that there's a lot of detail, there's a lot of complexity, there's a lot of information there, which has been generated at design stages to be able to infer how that building is going to be constructed. And it has been used for class detection and so on. And the problem is that all this data, when we start looking at them in more detail, they have quite a lot of issues. So we do class detection, we do quality control, but those data are not going to be perfect. So if we want to use them as they are, it's likely not going to be very useful. If we look at the MEP side of things, which is a different perspective around the building, the heating and cooling context, this is part of that federated build model, and you can infer what the complexity is. So this is just looking at the bottom part, and you can tell that there's much more complexity. And all that complexity has to do with the contextual knowledge around how that building is working and operating. And so we also need to be able to use that information to create knowledge graphs, to create ontologies, and I'm going to talk about that in a bit, because that's what MITRE is about. But what we find is that the data are not very good, and the data have a lot of issues. And the question is that in the real world, we always get this data, whether it is 2D drawings or whether it is building information models in more modern cases. We get other type of data, and all this data are always going to be problematic. So, what we have been working on, we have been working on algorithms and tools that are robust to such uncertainties. One proverbial case is around how we can generate and understand energy performance. And the way we do that, we set up energy models. So in early design stages or later design stages, for example, there is an ASHRAE standard 209 that kind of talks about different design stages. And there is a lot of discussion around how we use energy modeling. We need to create those models that are not correct, but represent our understanding and support not actual numbers, but support a discussion and a decision around how things are. So the reason why we create those artifacts are not models for the sake of models, but rather they are models to help us understand how specific design decisions are making and what the impact they have, and then drive that production between the different disciplines as a way of finding and exploring effectively that space and delivering solutions that are fit for purpose. So what we have been working on is around that question. Can we accelerate that process of facilitate that discussion? Can we support in a way a fast engineering and re-engineering so that you can get responses around how your building is operating or how specific design decision is going to be made? So we have been working on algorithms that automate that process, and the case of an energy model is one example. And this is looking at the geometry. For example, this is a building in France, a need from EDF. This is a UCL building. And we have been able to automate that process by using some input data that is the building information model, which is very imperfect, and then getting out something that can be simulated using something like energy class. Now, what becomes quite interesting in that case, and in fact I would argue in many cases, that when we look at understanding energy flows between buildings, this is very much a topological issue. We need to know this space, to what space is connected below, above us, or next to us. And so, when we have something like a graph representation, I'll explain what this is and I'll show you examples in a bit, that allows us to capture that complexity and capture that in a robust way. So what I'm introducing here, I'm introducing some sort of representation, which is a knowledge graph, an ontology, and we're going to get to that, that allows to capture how that building is connected. And this is the proverbial and fundamental information which is required so that we can generate some energy models. A second bit, which is equally important and relevant, and this is again academic work, but it has quite a lot of implications, is how we can look at the different perspective. So heating and cooling side of things, it's a different world. It's talking about the same context, which is the actual building itself, and how we can take that information and bring it over to the same, under the same umbrella and understand how we set spaces and so on. So what we have been looking at is developing different algorithms that automate the process from different inputs. In this particular case, this algorithm is taking building information modeling data, and then generating that connectivity that allows us to tell which terminal unit is connected and how connected to other systems. And then we can generate, again, some sort of representation around that connectivity. And the important bit is that that representation is going to be very different for this building to the next one, but the structure of that representation can be exactly the same. And so if we manage to do it for one building with a fixed structure, then we can do that for every building with any structure. So to highlight this is one example of that workflow, where we started from the different building information models. It was a federated model, Bartlett, and then managed to generate automatically or semi-automatically the image model. You can run that model, give some results back to the user, and then if the user decides to change one parameter, operation or otherwise, you can regenerate that automatically, and there's not a lot of effort into doing that process, which usually takes quite a lot of time. You have very fast and very quick responses to that. And so this is trying to automate that aspect. But I think where it becomes much more important is when we go to operation. When we actually have data, when we have data that are coming from the different aspects. And then we have different stakeholders, and they have different requirements, they have different needs, and we need to serve their purpose. So what I've chosen to focus on is one of them, and actually what I'm going to be talking, we can change the context in the stakeholder, and we can demonstrate the same ideas, I think that was raised before, and understand that while they are looking at the building from their perspective, they have the same needs of understanding structures and using the data. And so these are ideas of questions that might be asked from the facility managers, which is the UCL Estates team. And it is questions about the resource utilization, it is about compliance, it is about resilience, that was not before, it is about comfort, it is about energy use, it is about reporting KPIs for strategic decision making, and they have to do working with different types of data. Environmental data, access and occupancy data, utility data, and so on and so forth. So the question is, how can we do that? And the process, the way it happens now, there's a lot of value associated with data, so we didn't install 3,000 or 4,000 sensors in this building. But then accessing that information and finding useful information, getting signal from all that noise becomes very tricky, especially for people who are not trained to be able to do that. And the question is, how can we support that decision making? Again, we're not looking at the data as the data, but we're rather looking at the users and how we can support the users in making decisions and answering questions of the type that we look at here. So, what I'm going to show you is an example that is very relevant to this conference and this audience that looks at heating and cooling systems. But we can be looking at work orders, we can be looking at other stakeholders, and they have a very different set of questions. But what I'm going to tell you is going to probably be very similar on the baseline. And so what we have been working on, and I'll show you a demo, is we have been working on a data integration platform, or middleware, which works with built environment data of different types. So what I was talking about here is building information models based on the industry foundation classes. But we can take COBE, we can take PMS data, we can take 2D plans, we can take other aspects, and we can feed that into our platform. And what our platform can do is generate some sort of representation, which is that knowledge graph that is based on ontology. So an example of what was mentioned before. And that knowledge graph captures all the essential part of what the building is about in a way that is curable and discovered by the different stakeholders and by different analytics. So we can be running those processes, and then we can be collecting the data from the different assets. So this can be a BMS system, this can be IoT sensors, this can be weather stations, this can be APIs, web services, whatever. So we have a very generic driver architecture that allows us to get this data and access this data, and then cross-reference those two things so that we can support decision making. The way that's done, and the way it should be done, is in a universal way. So that knowledge graph, that ontology, supports a representation that has an immutable structure or a different structure. And so the way we should be able to expose those data to the outside world, which can be analytics, which can be AI, which can be users, is through standard interface. So I'm not going to go to the computer science bits, but using something called GraphQL, we can expose this information. And you don't really need to know about what building you're talking about. You can explore and you can ask questions around your data, and you can discover what the structure of the data is based on your ontology, and then you can access the relevant data using, again, that API without understanding which building you're working on. And that is very important so as to deliver and separate and develop services. So, this is an example, and I'm going to show you, this is an academic example. But I'm going to show you, and it's exactly the same idea as was mentioned before. The visualization context comes last and is not so important. It is important from a user perspective, but it is less important than the underlying data representation, which is based on these properties. So, here's an example. So this is kind of how our platform looks like, and it supports different data integration. But then this is what comes out. This is the graph of that building. There's a building, there's a level, there's a floor, there are spaces, there's a function unit, that function unit has points, and this structure is then fixed. So there was a question before, in our case we're using GraphQL, which is one graph database, but that gets generated automatically through processing the different data artifacts that are coming in. What now becomes quite interesting, and this is just graphics, the back end is working based on the knowledge graph, that is based on the ontology, is that we can zoom in and understand exactly the relationships and how things are connected. So the graphics are not as impressive, but for example here, this is a case of the function unit, and we're focusing on a specific function unit. And what you see here is the real-time data and historical data from the building. But what is more interesting is that we can take the local context and bring it into our LLMs. So our LLMs, for example, in this particular case, they're just interpreting the data. We're really feeding the data and analysis and analytics from the actual building, asset, and specific domain. So asking questions around how it's operating, asking questions around what we can do, if there is a malfunction, if there is something else, and then getting us answers that are specific to the specific role of the facility manager or the technician, or getting answers around specific about that specific asset that is problematic. So this is kind of showcasing different examples. So that was a function unit, but we can be focusing on VAVs, and then again, different set of analytics on the back end, different context on the back end, but through the graph and by querying, whenever somebody is clicking over there, we're exploring that hierarchy and then passing the right references, the right analysis tools, and then we can be exploring and asking questions around how our building is operating. And so, what I hope that conveys is not a focus or fixation around technology, but it conveys the message that we need to be able to sustain these dialogues and provide owners, operators with the right tools. And we have tools that we didn't have 2 or 3 or 4 years ago. And we need to be able to make their life easier so that they can take better decisions, and these better decisions are actually going to make a difference and make our business better. Thank you.